In this video, we're going to look at something called the method of initial rates. And what the method of initial rates is it's a way for us to set up an experiment where we can actually set the conditions just right so that we can measure m, n, and k. That's our goal with the method of initial rates. So from a balanced reaction, we can write a general rate equation, but we cannot figure out m, n, and k without more information. So what's going to happen is we get when you have something like this where you can only get so far just from looking at a balanced reaction, you then need to go and develop some kind of experiment that's going to allow you to actually get the values for m, n, and k. So let's take a look at the setup for this. And the reason why we call this the method of initial rates is because what we do is we set up an experiment where we change the concentration of a reactant. And then we let the reaction run, and we measure the rate very close to the start of the reaction. Now let me explain why we do it very close to the start of the reaction. The reason why is because if we do it very close to the start of the reaction, almost like within the first couple of instants that the reaction starts, so we're talking like right here in the reaction, right at almost time zero. The reason is because, in essence, the reaction has just started and essentially no A has really been consumed just yet. A teeny little bit has, but almost none. So what we can basically say is that the initial concentration that we start the reaction with is the exact concentration at which we measure the rate. Technically, it's a little bit of an approximation, but it's a very good approximation because we're doing it almost the instant that the reaction starts. So in essence, we're saying if we start the reaction with 2 molar, at that instant, how fast does the reaction go? If we start the reaction with 1 molar, in that instance, how fast does the reaction go? So I've set this up where we do that. I have the reaction of A goes to B. And again, this is just general. You'll see examples of this where we don't have A goes to B. But for this just general discussion, we have A goes to B. So let's do something simple first. Let's write a general rate equation for this. And that's going to be rate is equal to K times the concentration of A to the M, right? We don't know what K is and we don't know what M is. We got to do our method of initial rates. And so let's look in here and look at what's going on when we set up these reactions. So what I did was I set up a reaction where I had 1 molar A and one where we had 2 molar A. And now I'm going to go in and I'm going to measure right at that beginning instant, almost right when the reaction first starts. I'm going to go in and I'm going to measure my rate. And the way that I'm going to do that is I'm going to look at the tangent to the line right at that point. And I'm going to draw that tangent. So what we can see right away is when we draw these tangent lines, the reaction that starts with 2 molar is going to have a greater rate because the slope is much larger at that instant that the reaction begins than the one for the 1 molar. So the rate at 2 molar is greater than the rate for the 1 molar. So already that's kind of important for us to know because we change the concentration of A and we see that the rate changes. So that tells us that A has an effect on rate. So we know that M is not going to be 0 just from that. But now the question is, what is the M? Can we get the M from our data that's here? So in this chart right here, I started my reaction at 2 different rates. I went in and I measured the tangent to the graph. And I got my instantaneous rate. And what I see is for the 1 molar, I get a rate of 1 molar per second. And for the 2 molar, I get a rate of 2 molar per second. Now, will the numbers be this even when you actually do an experiment? No. This is just for demonstrative purposes. This is just to make a demonstration. But you get the idea, right? So we see that as A goes up in concentration, our rate goes up. And that's what we would expect. As we increase concentration, the rate goes up. So now let's think about what should happen here. Like if we look at this setup and we have M, the possible values of M are 0, 1, 2, or a half, for example, what would happen if we doubled the concentration of A? Like what would we expect to happen to the rate? Well, let's just figure out what actually happens in this case. So let's take our rate at our rate 1 versus rate 2, so our rate 2 divided by rate 1, and this would be 0.1 and 0.2. And let's compare that to our concentration of A2 over a concentration of A1. So our rate 2 in this case was 2 molar per second, and our rate 1 was 1 molar per second, so that gives us a value of 2. And our concentration here was 2 molar, and our concentration for 2 was 2 molar, and our concentration for 1 was 1 molar, so this gives us a 1. I'm sorry, this gives us a 2. So what we're basically seeing is that as we doubled the concentration, and this leads to a doubling of the rate. So the question is what M makes this possible? What M would lead us to the fact that if we doubled the concentration, we would double the rate? So let's plug some things in. So if we double our concentration here, so if we take our 2 and our order was to the 0th power, what would happen to our rate if the order was 0th order? Well, if we doubled our concentration and our order was 0, it wouldn't matter because this would give us a 1 no matter what. So if we doubled the rate, we would see no change. I'm sorry, if we doubled the concentration, we would see no change in our rate because the 0th order would make it so that there was no link between the concentration and the rate, because 2 to the 0 would just be 1 and our rate would stay the same. So now let's look at the possibility where we have 2 to the 1. So in this case, 2 to the 1 would mean that if we doubled our concentration, we would double our rate. This would give us 2. So a doubling of the concentration would give us a doubling of the rate. And if we had 2 to the second order, if we doubled our concentration, this would quadruple our rate. And then let's look at 2 to the 0.5. So if we go in and we take 2 to the 0.5, this would give us 1.41. And so that's what we would be looking for. So now the question is which one of these possible scenarios, 2 to the 0, 2 to the 1, 2 to the 2, or 2 to the 0.5, gives us back our change in the rate? Well, in this case, we would decide that it was 2 to the first order. So in this case, we would say that M is equal to 1. And that's how we get back our order from this data. So this gives you a general introduction to it, and this kind of sets it up. Now we're going to actually look at some real examples where the numbers are not going to be so even, and I'll show you how to go about doing that. But from this data, we were able to deduce that the M is equal to a 1 by looking at the initial rate versus the actual experimental rate. I'm sorry, by looking at the initial concentration versus the experimental rate. Okay, so on this slide, we have the method for how to go about doing that process. So this is called the method of initial rates. Now let's summarize what we did. So we wrote a general rate law. That was step 1. So we write rate is equal to K times the concentration of reactants to their respective orders. We choose one of the reactants and select true trials where the concentration of this reactant are different, but the concentration of the other reactant is held constant. So we're going to look at that. So in the first example we looked at, we only had one reactant, so there was only one possibility. We'll look at what happens when we have more than one reactant in another example. But the key here is you have to look for a control case where if you have two reactants and we want to figure out what's going on with one of them, we have to hold the other reactant constant so that that becomes a constant. And then we can just deduce what's going on with the other one. But we'll see that in an example. And then it says determine the order by looking at the relative change in the concentration versus the rate. So again, we're gonna talk about that when we get there. But what we expect for 0, first, and second order is, and these are general for doublings. So if we double the concentration, it has no effect. That's always for 0 order. For first order, if you were to double, it would double. And for second order, if you were to double, it would quadruple. Now, you're not always going to get doubling for these. You might get tripling or something like that, and I'm going to show you how to handle it no matter what. You're actually just going to test each one, so we'll look at that. And then you repeat the process to determine the order for the other reactants, and then we'll look at also how to get K. So when you want to get K, you write the rate equation, and then you select one trial, you substitute it in, and then you calculate K, and I'll show you how to do that in just a second. So we'll come back to this, but this method This is a good thing to have in front of you when you're going about these calculations, because it kind of sets everything up for you, and then we're going to look at it in more detail. So let's look at two examples where we have to use this method to come up with an answer. And the first one is simple, and the second one is more complex. So for the first one, it says determine the rate law for this reaction, CH3CHO goes to CH4 and CO, using the method of initial rates in the following data. So now let's set this one up. So step one is to write the general rate law. So in this case, it's going to be rate is equal to K times the concentration of our reactant, CH3CHO, to the M. We don't know what M is. In the data, we have the concentration of the reactant and we have the rates. So we're going to use this data to come up with it. So just like we did in the first example, we're going to take any two of these and we're going to compare and see what happens. Let's take trials 1 and 3. It really doesn't matter what trials you take. But the reason why I want to take trials 1 and 3 is because I think that's going to help you see what's going on a little bit better. Because that one is tripling instead of doubling. So let's do trials 1 and 3. So let's take trial 3 and trial 1. So what we're going to do is we're going to take the ratio of the concentrations, so 0.3 molar divided by 0.10 molar, and our ratio here in this case is equal to 3. So we're not doubling in this case, we're tripling. So this gives you a little bit different flavor for what might happen when you get real data. And now let's compare the rates. So we get, for this one, we get 0.182 molar per second, and we get 0.020 molar per second. And when you do this division, this is going to be about a factor of 9. So when you do that division. So when you divide 0.182 by 0.020, you're going to get 9 point something, but it's going to be very close to 9. So now what we have is we have a 3 and we have a 9. And the question we have to ask ourselves is, what order is going to allow us to, what order is going to explain this trend, where if we triple the concentration, we get a factor of 9 in the rate. So let's try some different things. So let's take our 3 and we'll set it to all the different possibilities. 3 to the 1, 3 to the 0, 3 to the 1, 3 to the 2, and 3 to the 0.5. We're not even going to have to do to the 0.5. So if we do 3 to the 0, that's going to equal 1. That does not explain the 3 and the 9. Let's do 3 to the 1, so m is equal to 1. And in this case, that's going to give us a 3. So again, that does not explain the 3 and the 9. Now let's take 3 to the second power. So if we take 3 to the second power and you plug that into your calculators, now you're going to get a 9. So this is the one that explains our data. So in this case, we can set m equal to 2, because when we triple our concentration, we get a factor of 9, and that is explained by an order of 2 because 3 squared is 9. So now we know that our general rate expression is rate is equal to K times the concentration of CHO squared. So one thing that I want to point out at this point is that, you may not get an even number like a 3. You might get something like 2.47 as your ratio of the concentrations. That's totally fine. All you would do is you would take your 2.47 and you would try the 0, 1, and 2 power and see which one of them gave you your ratio for the rates. So you can use this method even if the numbers are not totally even. In the second part, we have to figure out what the value for K is. And what we're going to do is we're going to take one of the trials. It doesn't matter which one. You can pick any one you want. You're going to get the same answer with an experimental error. And we're going to plug it in. So we're going to take the value for the rate. So we'll take trial 1, for example. So we're going to take 0.020 molar per second is equal to K times the concentration of 0.1 molar squared. So, and this is an M. So what I'm going to do now is we're going to solve for K, and that's going to equal 0.020 molar per second divided by, and then I'm going to take 0.1 molar and I'm going to square it, and that is equal to, so we get 0.020 molar per second divided by 0.01 molar squared. So I squared the value and I square the unit when I do that. Okay, and then we just do our division. So we have our little k is going to equal, and when you divide 0.020 divided by 0.01, you get 2. And then we have to deal with our units. So our units are molar per second divided by molar squared. So when you do that, that's going to be, let me just clean that up a little bit. So we have molar per second, that's on top, and then it's divided by molar squared, or the way to think about that is 1 over molar squared. We can multiply it by 1 over molar squared. So that's basically putting the molar squared on the bottom. And so when you work the units out, the molar is going to cancel on top, and we're going to get rid of the squared. So this is going to equal 2 times 1 over molar seconds. So when you cancel units. So you got to cancel the units and be careful about that. So if you have molar per second divided by molar squared, when you have something that's on top and something that's on the bottom, this is basically like saying that you're taking molar per second and you're dividing it by molar squared. So the way to think about this is that this is 1 over molar squared is the multiplication. So you can kind of bring it up and have it as 1 over molar squared. And then when you cancel the molar, in essence, there are 2 m's down here on the bottom. So this is molar times molar. And one of those goes away, and so you get 1 over molar seconds. So you have to practice canceling those units. Another way of doing this is to think about what you have to do in order to get the correct answer. So if you look at it, what we have on the left, so if you take the rate equation, so we have rate is equal to K times the concentration of CH3CHO squared. So over here we have molar per second, and our units of molar are going to be molar squared. So the question is what units do we need for K? Well, in order to get the molar per second, we have to have 1 over seconds for sure for K, because that's going to put the seconds on the left. Now we have to deal with this molar squared. So to get rid of the molar squared, we have to put an m on the bottom also. So the correct units for K is 1 over molar seconds, and you can see that from this, or you can just solve it over here by looking at the actual units when you solve for K. So this is going to have units, this is going to be a value of 2, 1 over molar seconds. This one has 2 reactants, and we have to figure out the orders for both of those. So we have rate is equal to K, the rate constant, times the concentration of ClO2 to the M, times the concentration of OH minus to the N. So let's start with the ClO2. So now here's the problem with the ClO2. We have 3 trials, and we have to decide which 2 we're going to pick. So let's look at the OH minus concentrations. And if you look, there are 2 OH minus there are 2 trials where the OH minus stays the same. Now this is good for us because in essence, if these 2 are held constant, we're only looking at the effect of the ClO2 on the rate. So what we're going to do is we're going to pick trials 1 and 2 for the ClO2 where the OH minus concentration is the same. So in this case, we're going to get 0.060 molar divided by 0.020 molar, and this is going to give us a 3. Now let's look at the relative rates. So we get 0.248 molar per second divided by 0.00276 molar per second. And so in this case, this gives us a value, an exact value of 8.985. And so in essence, we can sort of summarize this as 9 within experimental accuracy. So now again, we have to do our trials. So we have to see which M allows us to do that. So we we tripled our concentration in this case, and we have to see which one, 3 to the 0, 3 to the 1, or 3 to the 2 is going to give us back. For tripling, we get a factor of 9 for the change in rate. So in this case, we're going to get a 1, so it's not 0. In this case, we're going to get a 3, so it's not to the 1. In this case, we're going to get a 9, so we're going to say that M is equal to 2. Okay, so for the second part, we're going to look at the OH minus. we have 3 trials for OH minus, and we're going to look for 2 trials where the concentration of ClO2 is held constant. So the 2 that we're going to work with are trials 2 and 3. So in this case, and whenever you do this, I always recommend taking the trial that has the highest concentration divided by the trial that has the lower concentration. That's just going to give you nice whole numbers and not fractions. But you can do it either way. It really doesn't matter. You could do it the other way and still do your tests just to see. So let's look at this one. So we have 0.090 molar divided by 0.030 molar. And that's again going to give us a factor of 3. So we're tripling our concentration. And we have 0.00828 molar per second divided by 0.00276 molar per second. And when you do that division, that is going to give you a 3. So now let's do our tests. So we have 3 to the 0, 3 to the 1, and 3 to the 3. 3 to the 2. And at this point, I think you guys are going to see that it's not to the 0, and 3 to the 1 is going to give us 3, so the n in this case is equal to a 1. Okay, so now let's determine the value for k. So we're going to pick one of the trials. I'm going to pick trial 1, and I'm going to plug everything in. So to determine the value for k, we're going to say the rate is 0.0248 molar per second is going to equal k times the concentration of ClO2 squared, which would be 0.060 molar squared, times the concentration of OH minus, which would be 0.030 molar to the first. So when you solve for k, you get 229 as the number. Let's look at solving the units though. So what we have is we have molar per second, and we're going to divide that by molar squared times molar, or molar cubed, right? Because I'm going to bring down the molar squared, and I'm going to bring down the molar. So we have molar per second divided by molar squared divided by molar, or in essence, this is the same thing as saying molar per second times 1 over molar cubed, because it's molar squared times molar would give us molar cubed. So in this case, we get a value of 1 over molar squared seconds as our units. So if you'd like to see that done the other way, we'll do that over here. So on the left, we have molar over seconds. We have our value for k, which we got to figure out the units for, and then we have molar squared times molar, or in essence, we can summarize that as molar cubed. So for our units of k, we definitely have to put seconds on the bottom. And then to get it as molar over seconds, we're going to have molar squared down here, which will cancel out with the molar cubed to just give us molar seconds on the left. So the correct answer here is 229 1 over molar squared seconds. And so that is how you do the method of initial rates. Now there's one problem in the textbook that's really, really good that goes over this, and what's going to happen is you're going to get data, but it's not going to give you all the data you need. There's going to be a piece of data that's left out, and you're going to have to think creatively about how you can solve the problem.